discuss very little that I know of this subject. My expertise ends at considering neutron stars as point particles. So I will be directing the questions related to the macroscopic properties of neutron stars to the organizers and the audience. But I'll try to highlight a few things that the collaboration has found, and I'm part of that collaboration. And also a quick analysis that we recently did by using some of these results. Now, what we have on screen is essentially a snapshot from a simulation. It's not a full GR MSD simulation, but rather a GR simulation and a matter simulation separately. So on the right, you have how the matter density evolves as the two neutron stars come closer and merge, and on the left you have the emission of gravitational wave from the binary system. Now this is the publication that reported the discovery of the first binary neutron star merger, and what we see in the figure is essentially the track that a gravitational wave merger event leaves in the detector data. It's a signal that ramps up both in amplitude and frequency. On the y-axis, the frequency have been plotted, while the normalized energy represent the amplitude of the signal that is there, and it increases from blue to yellow here. Okay. Just a couple of things to highlight here. While I'm sure, the audience here knows about this event much more than I know, but I just wanted to highlight a couple of things. So this was a signal with significant strength. We call it signal to noise ratio of 32, which is quite high, thanks to the closeness of this event. So this event was detected at 40 megaparsecs, closest gravitational wave event we have detected so far, including another binary neutron star system. And if I'm not wrong, this is also the closest short GRV that we have detected. So due to that, we have very high SNR event, and that helps us exploring the properties of this event in great length. And the second thing is that I want to highlight is the statistical significance of this event, which is less than 1 in 10 power 5 years. Okay, it just means that there is 1 in 10 power 5 chance that only 1 in 10 power 5 chance that it can be a false alarm and not a real event. So statistically quite significant event. Now, again, as I said that most of the audience might know the properties, but I'll just walk us through some of the aspect which may be useful in discussing what I want to present here. And one of the things that I want to highlight here is this is the chirp mass. It is a combination of the component masses, a special combination of component masses, and this is the best measured parameter for any gravitational wave event, not just this event, but any gravitational wave event. And this you can see from the error bars, which are very low, and this is our best measured parameter. Now, when one comes to constraining the component masses, it's not as accurate as the chirp mass, and the reason being that the component masses are correlated with their spins, and that leads to the measurement not so good, not at the same level as the chirp mass parameter. And also it's the chirp mass, the mass ratio information which leads to the constraining of the component masses also is subdominant, as we'll see in the structure of the waveforms. Okay, so that is one point. and this is indicated in this plot. So on top we have the constraints on the two component masses, and another thing that I wanted to point out is here the results have been presented for two sort of situations. One is when we assume that the involved neutron stars do have small spins, and we limit the value of this small spins to be 0.05. And the reason for choosing this configuration is essentially the observed double neutron star systems. If you take an example of the most relativistic double neutron star system that we have observed so far, or that is going to merge within the Hubble time, if you evolve its spin, it turns out to be 0.04, okay? And that is why the constraint on the spin parameters here. The more conservative constraint comes from the equation of states, and that is at the level of 0.9, okay? But 0.89 that we have here is also the limit of the waveforms that we have, which can model spins to this level, okay? So it is a combination of both the equation of state requirements as well as the ability of waveforms to probe such high spins. And these are the two spin priors we use for constraining the properties of the two neutron stars that we have observed, or the merger of the neutron star that we have observed. And hence, like, we list all the properties for these two particular cases, okay? So what I want to point out is first, sorry, I went ahead in my slides, apologies for that. So I said that the chirp mass is the best measure parameter, and it's not correlated with the spin, and that is what we see here, that its constraints are almost the same for both the spin choices. However, if we look at the constraints on the component masses, M1 and M2, then we see that the upper bound on the masses is different. So since this is a more conservative choice, you get a broader constraint on the component masses. And the same goes for the second mass. Equivalently, you can also see, if you look at this mass ratio, that is constrained between 0.7 and 1 being for the equal mass system, 0.7 of course is the asymmetric system. If you consider the priors, which are as small as, or the limit on priors as 0.05, then you constrain it better than when you can constrain. And again, of course, it has to do the same thing, because the spins are correlated with the mass ratio, you get poor constraints when you go for the more conservative choice, which is this. But if you stick to, this is actually not a very, this is also motivated by the observations that we have so far, and also equally realistic in my opinion. There are two more things that I would like to highlight is on this slide, and that is the measurement of the tidal deformability. Okay, so the extent to which the companion's gravitational field deforms the other neutron star is measured in terms of some parameter lambda. We'll see a definition of it, and we use gravitational wave observations to constrain it, and these are the constraints on it. Of course, in your 0.05 spin priors, as well as with more realistic priors. And although tidal deformability is also expected to be correlated with the spins, and that is what the effect that we see here, that it is slightly changing when we go ahead. But it's not the only measure. There are multiple ways in which we try to constrain this deformation of neutron stars, and we will see one by one how it goes. Right, so this is essentially, that's what I discussed. The only thing that I want to highlight is the two-dimensional contour that we have in the M1, M2 plane represents the measurement of the chirp mass. And the shape of this is decided by, as you can see, the combination of both the masses. And the fact that it is the best measure parameter is reflected in the fact that it's a very narrow line. But the extent, you can see, for the low spin priors, we have constrained the Chirp mass to very, very narrow regions, and the values which are here. Right. This is an additional detail, but it's probably very relevant for the parameter estimation studies, and that is that we identify a combination of the spins and the mass ratio which aptly represents effectively the spin of the system, okay? And this is also probably the second best measured parameter that we have in general in binary neutron star or binary black hole system. So this is the combination. It's a simple combination of spins and mass ratios, and a value 0 would mean a non-spinning system, while it can take value of -1 and +1, where the two extreme mean that the spins are anti-aligned to the orbital angular momentum and spins are aligned with the angular momentum, orbital angular momentum. Right. Now, coming back to the question of constraining the tidal deformations, in fact, these are the 90% bounds, the dashed lines that we see here. They are the 90% bounds. The other dashed line is the 50% bounds on the individual tidal deformability. So both neutrons are deforming each other, and then you try to measure independently the two tidal deformability parameters, characterizing the deformation as the binary merges or as the binary approaches to the merger. And what is also plotted is this shaded region, which is essentially has been obtained by solving, let's say, TOV equations for different representative equation of a state. And as we can see in the figure, it has been highlighted that the observations which bound to 90% level the tidal deformability in this region do not favor less compact objects. Okay, so the equation of states that suggest less compactness, but they favor more compact objects. Okay, and that's seen in both the cases. So yes, so this is again the high spin prior or the more conservative prior, and this is the low spin prior, and the constraints are related. Now, this was the first event. We also have a second binary neutron star merger event identified to the best as BNS merger, although the possibility that it could be a very low mass black hole merger or black hole merger or neutron star black hole merger is also not ruled out. But it's a very good likely, it's very unlikely that it is going to be not a BNS merger. Why we couldn't confirm? Because we didn't have electromagnetic counterpart for this. And why we didn't have, I think the audience here knows better than me, but one of the reasons that one can argue is maybe the line of sight is it's an off-axis event, and the line of sight is not along our line of sight. So sorry, our line of sight is not along the EM emissions that we have. But that's the extent I can claim. But otherwise, there are many other factors. It's a very distant event. It's not like 40 megaparsec, but it's 160 megaparsec, and that reduces the SNR for this event from 30 to 10. Okay, and that is a big constraint because we do poor measurements of all the parameters when it comes to a low SNR event, including the tidal deformability parameter. Nevertheless, the masses are again constrained. These are slightly heavier. This is slightly heavier than the first event, and these have significant consequences to the measurement of tidal deformability parameter for the reason that heavier the object, less compact it is, which leads to low value of tidal deformability parameter. And as you'll see that a low value for this tidal deformability parameter is a hurdle in measuring these parameters. We'll see the waveforms, exact waveform which will reflect this particular aspect. The mass ratio measurements are not very different from the one that we had from GW 170817. The effective spin parameter, as you can see, it is consistent with the low spin priors, even for the conservative case. And as expected, the chirp mass measurements do not change a lot. And there are constraints for the tidal deformability parameters, but these are also as I said, like, this is a heavier, it involves heavier neutron stars, and hence constraining the tidal deformability parameter is slightly difficult in this case. Plus it's a low SNR event, so all combined we have poor measurement of the macroscopic properties of the neutron stars from here, and you can see the constraints are slightly larger than what we had expected. So it includes more equation of states than what is predicted by the observations of the first. Now this is sort of a summary of the tidal deformability measurements that we have. So the pink and the green shaded regions are the measurements of the masses using GW 1708. So the pink is GW 17017, and the green one is for the second BNS event, and as you can see, the masses are constrained to higher values. And the vertical arrow that you see essentially is the bound that we got on the tidal deformability parameter, which was denoted by this, this lambda tilde parameter. Okay, the second row actually, I think it's slightly weaker, but yeah, this is the row on which the measurements are about 800. The plot is for the low spin priors only, so we have to look at the low spin prior values here. Right. So, so this is the constraint, the upper bound on the lambda values, or lambda tilde values from the GW 170817 event. Here, the author has not plotted, maybe just to avoid any overselling of the constraints from the BNS, gravitational wave BNS events. Now, this is, of course, the upper limit, like these two neutron star systems, they are sort of upper limit, observed upper limit for the neutron stars. While there are equation of states which do suggest, so all these gray lines are representative constraints on the masses from different equation of state, and I think there is nothing much relevant, but this green curve that we see here is essentially the double neutron star population in the galaxy, and this is the orange curve is a bimodal distribution that also includes the neutron stars in X-ray binaries or with the white dwarf. But nevertheless, the estimates seem to be consistent with both the models. There is these dashed lines also, which sort of tell how lambda changes as a function of total mass, and this is sort of indicating that it is more close to m power minus 6 than m power minus 5, a very small observations here. Now these tidal deformability measurements also can be translated into constraining the radii of the neutron stars that are involved. Now in this plot, there is an assumption which has been made that both the neutron stars are sort of identical in a sense, like both of them follow the same equation of state and have the same properties. And then two independent methods were employed to constrain the radius of neutron stars. And this is a paper which focused on the measurement of the radius and the equation of state. And I wouldn't go into the details, but this part is more agnostic to the equation of state, whereas this one takes into account in a finer way the information that is going to come from the equation of state, in a sense that it parameterizes the pressure density relation itself. And while both constraints are similar, it seems that the second one is slightly more constraining than the first case. And what we have on blue is, I believe, it's the lowest spin priors, and the orange is for the high spin priors. Okay, so this is the mass radius relation or observations that we have from GW 170817. We don't have a similar study for the other one because it will not probably add a lot to our understanding of this thing. Now, coming back to so this is what was done so far. And while the constraints are not super tight, they start to come closer to the constraint that we have from, let's say X-ray observations. Okay, so maybe after a few more events, you can combine this information and get better constraint, but it is coming closer to that. And in that light, it is probably important to look at the timeline of the GW detectors that has been proposed. Of course, this is subject to many other things. For example, COVID delayed the operations for significantly, or cut down short the runs. But nevertheless, this is our optimistic timeline for these observations. So we just finished what we call the third observing run, or O3, and now we move to the next observing run, O4, which was supposed to start around March this year, but it's been delayed for a couple of months. Likely it will start in May for sure. And as we can see, is so what we see here is the sort of horizon for these detectors, assuming the sources are binary neutron star mergers. So this is sort of the distances up to which you will be able to observe the neutron star mergers with some threshold SNR. And as we can see that this range is the lower reach, or the lower horizon is going to change by a factor of 1.5. Okay, so that means if you detected 2 events, you are going to detect 3 events in the O4 PSD. Okay, and subsequently, I think late in 27, you will have O5. So this is called A+. This is called advanced LIGO, and this is called Voyager. Okay. And this again is going to change 2.5 times. That means 2 versus 5 detections in O5 and 3 detections in O4. That's typically what this means. Exactly. And similarly, the other detectors ranges also, but it's likely only Kagra will be able to operate. Virgo will be able to operate at O4 level sensitivities only in Voyager. But nevertheless, we have two detectors, and we have seen, at least in the case of binary neutron star merger, that even if the detector is not sensitive enough to detect the signal with confidence, it can be used to, let's say, localize the source better. And that's exactly what happened the GW170817 was not detected in Virgo, but it helps us localize the sources because the directions can be combined into the other information and constrain the source in the sky better. So with this, what we expect is that the mass radius relation will be constrained further. Our simulated or some sort of target region, the value or the equation of a state is sort of the pink line, and then it's been shown that how subsequent science runs will try to approach it as we go along. And the cyan is the current sort of constraint. It's like, again, one is making some approximations that the equation of a state is same for both and so on. And again, this is low spin prior estimate, but these are the constraints that we have. And if we go to the projected O4, that is this green shaded region, and finally the O4 will constrain better. So what we see here is with upgrades in the detectors, you are expected to constrain this mass radius relation more and more, and I think this is quite a lot of improvement anyways. If you detect something in this range, it's narrow. Now what makes neutron stars very special is just the duration for which we can detect them. Okay, what we have here is first five events. In fact, this has been converted into gravitational wave event now. First five events, these are the expected waveforms, and the longest one was less than 2 seconds long. So we saw this longest BBH merger, which was about 21 solar masses, less than 2 seconds in our detectors. But the neutron stars are light systems, so they enter the detector at the same time, but they merge at much later frequency, a much larger frequency. And as you can see that the waveform of the neutron star merger compared to the other waveforms, and it just goes on for a minute or two. Okay, we did have 100 seconds of data. I think here we have about 50 seconds. But it just tells that if waveform is going to be your tool, these are the sort of events that you should be after, because you can constrain so many parameters with such long waveform. And we are talking about long because other waveforms, even the lightest BBH merger that we had observed until these 5 events was about 2 seconds, while this is about 100 seconds. So you have 50 times more length of the signal that you can. This gets boring with the thing, but it just shows the and it's real time. Okay, so it's not slowed, it's real time event. So I think about 55 seconds, and now you have merger. Okay, so the last 55 seconds were recorded and plotted here, and this is also very crucial for BNS mergers in a sense that the tidal effects only become apparent after, let's say, 600 hertz or something like that. And if you have a light BNS merger, you get to see a lot of cycles when the tidal deformations are taking place. So this is also relevant for the discussions that we are having here. Now, going into the details of the measurement of these parameters, okay, I did not explain a lot how these measurements are done and so on, and I will not be able to do this in this talk, but I would just try to sketch the kind of quantity that we are trying to measure here. So this is a typical frequency domain phase of the gravitational wave signal, and it is this information that is most crucial when it comes to the data analysis of gravitational wave signal. And that's why when the waveforms were constructed in the era prior to the numerical simulations and so on, they kept this phase information as accurate as possible, because a loss in the phase information can can lead to the loss in detection. Okay, even if you for a BNS event, even if you are unable to model the phase with an accuracy less than one cycle. So for example, if you model the phase, but if you are missing the phase by one cycle, it can lead to non-detection. And that's why this phase was computed to very high order of accuracy using post-Newtonian formulation. What we see here is the powers of V. Okay, it's actually a series expansion in V. V is sort of expansion parameter, and the powers of V denote the post-Newtonian orders that we have. So for example, the terminology is 1 pn correspond to a correction of V square, 2 pn will correspond to a correction of V power 4, 3 pn will correspond to V power 6, and there are half pn terms also. So for example, V cube will mean 1.5, V5 will mean 2.5, and so on. So that's the terminology, but these results are expressed as series expansions in this expansion parameter. It's a dimensionless parameter, and essentially it's a function of frequency. The larger the value, larger the frequency at which the binary is orbiting. And so here, since we are interested in the tidal effects, I have split the waveforms into two pieces. One is what is computed. So the phase is computed using some energy balance equation, where you say that the amount that is lost, the amount of energy that is lost in gravitational waves essentially is amount by which the energy of the system is reducing. And using that argument, you can compute the phase of the signal, and this is the part which assumes that the neutron stars are point particles. Okay, the same waveform is for black holes, naturally, because black holes can be taken point particles as long as we want. The tidal effect is the one that comes into picture when you go beyond this point particle approximation and assume that, like, they are not point particles but extended objects. However, as I tried to indicate that, like, it's only much later in the evolution that the tidal effects become relevant, and the reason is that when the neutrons are far away, you can, of course, approximate that in point particles, but when they are closer, almost the sizes of neutron stars, at that level you cannot consider them point particles, and you need, but at that level already the frequencies are very high. So you can see that the contributions that come are of the order of V power 10. Now typically the neutron stars, let's say, reach of the frequency of 0.1 or order of 0.1, and that means 10 power minus 10. So you can see it's a very small effect, and this was the reason why this lambda tilde parameter has to be very large. So for the second BNS event, which included or involved neutron stars with heavier masses, the value of this parameter is lower, and hence it is harder to measure in a parameter estimation problem. Nevertheless, just to give you a sense of how much it is, essentially, if we can calculate, let's say, how much dephasing will occur if you consider the tidal effect. So this calculation assumes a very simplistic scenario where you have two neutron stars, and you compute the phase up to the point that the two neutron stars are in contact, and it assumes some typical values for the love numbers K2 and the compactness C. Let's say, I think, what's the typical love number value of K2 for 0.01 or something, or I don't know, I don't remember, but compactness may be 0.15, and if you just combine those values, you get about 14 radians, which is nearly 3 cycles. And 3 cycles, as I said, like even one cycle is crucial. 3 cycle is something that you can definitely detect and measure, and that's what we have been after. If you plot them, this is not the same waveform that I showed. It's slightly more involved, although the information in the tidal terms is not very advanced in the other waveform. But it's a complete waveform. This is an in-spiral waveform, and for BNS mergers it is good enough to work with in-spiral waveform. In fact, the GW170817 event was analyzed using an in-spiral waveform, including the tidal effects, and when we repeated the analysis with more sophisticated waveforms like the ones here, the results were not very different. Okay, it's at the level of 90%, they all agreed. And so this is some sort of depiction of how the waveforms change when you have neutron stars with larger and larger deformation possibilities. Okay, so for example, larger value of lambda will indicate that the neutron star can be deformed more, and as we argued that, like, larger value of lambda also helps constraining it better, because the fact that, like, this is a very high frequency term. And the top is essentially the time domain waveform, the bottom is actually the frequency domain waveform, the same thing, and it just shows the kind of dephasing that you will see, and it becomes more than 2 or 3 cycles when you go all the way till the merger. In fact, this waveform was truncated at the time when the amplitude sort of peaks. So it doesn't include the merger part, but at least goes all the way till you can, as far as the in-spiral is concerned. Now, this particular lambda tilde parameter is a special comp. So we looked at the measurement of lambda 1 and lambda 2, where we independently varied or sampled lambda 1 and lambda 2 for the two neutron stars. But we can also try to measure the combination, that is lambda tilde, and this is the combination that appears in the waveform. So you can suitably model a combination of lambda 1 and lambda 2, and then try to constrain this instead of constraining 2 parameters. Okay, it's always good to constrain 1 effective parameter as compared to 2 parameters in a parameter estimation problem. And this is what our results are. So as you can see that this magenta is the in-spiral waveform, which was used for the first analysis, and then it was repeated with other variants of the waveforms, and the results are more or less consistent. There are changes in the bounds, but the bounds are not bounds do not change much, and this shows the level at which we can constrain this lambda tilde parameter, and this is what this is the only parameter that one aims to constrain, let's say using or one tried to constrain using the gravitational wave observations we have so far, because this is the leading effect. If you can't constrain it well, you can't constrain the remaining that come at higher order. And this, of course, naturally is because of the tidal effect corresponds to the quadrupole. The next order terms will involve octopole and current quadrupole and so on. And this is, in fact, it is completed. In fact, the post-Newtonian theory, in fact, Guillaume is here among us. So this writes the full tidal phasing up to 2.5 pn order, and it sort of parameterizes the tidal corrections in slightly different parameters, the mu plus and sigma plus, but mu plus 2 is essentially can be related to the lambda 2 that we had, or the quadrupole tidal deformability parameter, where the sigma 2 corresponds to the current deformability parameter, quadrupole deformability parameter, and then you have also the octopolar corrections. Okay, in fact, the quadrupole contributions also have some sort of asymmetric combination. In fact, you can combine plus and minus to write in terms of symmetric and antisymmetric part, and asymmetric part always appears with this delta. Delta is essentially a ratio between the difference of the mass component masses divided by the total mass. Okay, so it's a difference mass ratio parameter. It is 0 for equal mass, and non-zero for the unequal mass case. But you can see that if you have nearly equal mass neutron star, all these contributions that appear with this delta can be assumed to be very small or zero. In fact, for equal mass it is exactly zero. Nature doesn't produce exactly same mass stars, but you can say that, like, okay, given that there is not much variation in the neutron star masses, for black holes it may be relevant, but for neutron stars they are always very small contribution. And hence you can try to characterize the tidal deformability in terms of the quadrupole tidal deformability parameter, or current quadrupole parameter, or the octopole variant of it. And we tried to do that. We tried to actually project this earlier formula or earlier parameterization in the language of the parameters that was measured. That means this lambda 2 and so on. So until now, so the BNS, so just to indicate that the current constraint on the equation of state involving all the models, apart from a few, do involve only the 1pn formula, that is it involves corrections only up to v square. Okay, this paper is only in oh, I'm sorry, I have to get used to, this is in 220, so of course all the results were obtained before that, and but now we have we can go beyond the 1pn term and include the 1.5pn, 2pn, 2.5pn, and this is essentially the reparameterization of the previous result that we saw. And we try to measure all this, okay, but unfortunately it seems that so as we argued that this is a v power 10 correction, already very small, and you need large value of lambda parameters to measure or constrain this better. Think about going beyond v power 10 to 12, 13, 14, 15. So it becomes harder and harder to measure parameters which appear at higher post-Newtonian orders. And hence we'll have to be more realistic. We'll have to essentially try to use all the information that is there in the waveform, but then not try to measure all parameters that are there, because then there are correlations and the measurement becomes poor. And that is, keeping that in mind, we try to we try to have a parameterage which is much simpler than the full parameterization, where we essentially say that we can assume that the contribution from the small the contributions from slight asymmetry in the BNS system, they will be very small, so I can set them all to 0, and hence I get rid of all these parameters in some sense. And I also do not intend to measure in the first go the octopolar term or the current quadrupolar term related to the tidal effects, and hence my parameterization becomes this. So essentially what I have done, I have extended the 1pn relations that we had to 2.5pn, but characterized only in terms of the quadrupole tidal deformability parameter. So I'm still measuring the same parameter, but I am using a more accurate formula. And what we see is, like, if the waveforms are not accurate, it can lead to systematic errors, not just in the measurement of the parameter that you are interested in, but other important parameters like masses and spins. Okay, so it is important to use the full information in the waveform, and this is one step in that direction, where we complete the formula, assuming that, like, the only formula relevant, so only the term that is relevant for us is the quadrupolar term, and we use a full formula. And this is sort of, a table gives, it's an approximate number, but the improvements can be taken as real. Okay, so these are for the first BNS event, GW170817, SNR of 35, okay, in both cases. So the phasing, if we change phasing, the SNR doesn't change, because like the phasing cancels out from the absolute, and hence the SNR is same for the events. And what we have on the top is essentially the measurement on the relative error on this lambda 2 parameter. Okay, so in some sense you can say the error on the lambda 2 parameter is about 31% when we used 1pn formula. Only the terms, sorry, oh my god, right, only if you constrain this waveform to this formula, then you get a number, and then you use the full formula and get another number, and you can see the numbers are changing from 31% to 26%. A small change, but this is for advanced LIGO detectors. You may have future versions where this change can be larger. And what I have included here is some sort of systematic error, in a sense that if you had not included these additional terms, what is the systematic errors on the measurement of the lambda parameter, and here also it reduces once you use the full waveform. Then you, oh, this is a project, I mean, to find, right, yeah, so this also reduces. And in the last, I just show some sort of a number to indicate the accuracy of the analysis. Okay, so this analysis is done using Fisher information matrix approach, and we have to invert the Fisher matrix in order to get the errors. And this is the one way to check how good the inversion is. Ideally it should be 0, but in real life it is never 0, and the smaller it is, better it is. I think the acceptable number is depends on the person. Okay, so for me it's fine, but a person who needs more accuracy may even go further down this. So this is sort of I'm sorry for this, I'm still finding my way. Right, so, and this is the second event. So the last 2 rows are for the GW 1905-0425, and we see that here also the errors reduce. So essentially, by using more accurate formula, I am able to constrain the parameter better. This is an exercise where I essentially use different detectors. So I use advanced LIGO and O4, that is A+, Voyager, that is O5, and also a 3rd generation detector, Cosmic Explorer. And as we can see here is the SNRs go up as we go further and further higher in the detector configurations. This is your advanced LIGO number, this is A+, this is Voyager, and this is CE. The SNRs, typical SNRs are of the order of 30 for A LIGO and are of the order of 1000 for, and this all is going to contribute to the measurement that we see here. So as a function of lambda parameter, as you can see, it's monotonically decreasing values, and the same thing is also plotted against the masses. There is a gap at 1.4 solar mass, because in our parameter estimation exercise we consider the difference mass ratio parameter, which is 0, and you are supposed to take derivatives with respect to it and so on. So it leads to you are not able to do this analysis for this event. So 1.4. So one thing I will mention that, like, the configurations involve one neutron star with 1.4 solar masses, and the other neutron stars can have masses between 1 and 2. And we are using this work, the data from this work, which actually gives us not just the quadrupolar tidal deformity parameters, but also gives us octopolar and the current quadrupolar parameter. So we are going to use this to understand. The second parameterization, and I'll just wind up very quickly, is slightly more complicated. We now remove all the delta terms, but we keep the octopolar and the sigma terms. And finally, the third parameterization is the full thing. And what I want to show is, like, how it changes, how the measurements change as we change these parameterizations. So the first two parameterization where we neglected in both cases the asymmetric pieces, and this is for advanced LIGO, so this may change for future detectors, but for advanced LIGO, going from one parameterization to the other where both octopolar and current quadrupolar components were included doesn't change much. However, if we use the full parameterization, that the asymmetric pieces, then we start to see that the errors become actually larger. And this is, while I have not thought so much about it, but this is, I can understand that the mass ratio is correlated with other parameters, and that is what leading us to the poor measurements. But if you stick to away from the exactly equal mass case, for which anyway we cannot handle anything, we do get more or less similar estimate, but of course there are some changes. And this is an important message. Maybe we should include all these parameters in our analyses so that we get more realistic bounds than we have now. So with this I'll end with two short notes. Essentially I have said it already in the talk. So one is that the two BNSS events, or at least let's say one BNS event, has provided constraints which are not extremely tight, but they are slowly, with certain assumptions, they seem to be agreeing with the current observations. And although the second event could not contribute much to this knowledge for obvious reasons, of course, the constraints are still consistent with the previous thing, so that's a good check. And finally, that we have now more additional parameters, additional effects that have been modeled, and all the future analyses should be done with these modified waveforms, and hopefully they will give us better constraints on the equation of state parameter. I will leave you not with the summary slide, but with I showed a snapshot of a simulation. I'll just run that simulation. On the left you have matter density evolution, on the right you have gravitational waves, but I'll be happy to take any questions at this stage.
Okay, thank you, Chandra, for a very nice talk. So questions? Please raise your hands. Yeah, Gopu? Yeah, actually, any questions? Okay, maybe someone who's not asked questions would like to go first. Any questions? Yeah, Jaikum.
So the tidal deformity constraints which you give, the number which you give, so how sensitive are they to the equation of state itself? Are the error bars very much different if I use a different equation of state?
Right. For example, this the pink line that you see is, let's say, one very good choice of equation of state, and the bound that we have is the gravitational wave bound. Okay, so the Cian bound that we have. So yes, it is consistent with the equation of state that is most possible, but it's not very constraining at the moment.
Again, how do we select that the pink? The equation of state for this pink.
Well, I think it's just it's one most favored choice. I think nothing else. There are in fact, this is a very special plot, but these are the constraints, for example, from all different values of equation of state. So it can be anywhere in this, and here also you can see that it is right in the meat of this gray thing. So far so good. Yeah.
Okay. Any other questions? Okay. Yes. Ashok.
So, I have a quick question. That slide timeline. Yeah.
with this one?
So, yeah. So I'm a little bit confused about Kagra. Means how can it sees the very close? Means you have purple and gray. So I think not the O5.
Oh, this one.
Yeah. So it seems purple is very high, then mid. Then how is possible for the detector? It is seeing the close region, then middle distance.
Sensitivity increases, right? It's noise. They are reducing the noise floor, so sensitivity increases with time. I think with upgrades.
Yeah.
So why there are gray in between?
I think the gray is when it is not probably planned upgrades in between.
Yeah. So
it is not taking.
During offer, take a break, upgrade, then you already with better sensitivity, and that's what it shows.
But say first it was seeing 1, 2, 3, right? Okay. Then it will see up to 10 kpc, but the mid region also it will see, right?
No, this is timeline.
This is just, I think the gray represents that detector is not taking data at all.
Okay.
So that's 18 months of time, and it's various stages they will be going.
Oh, okay.
Yeah.
Yeah. So
And it's
it's
the same, but it's factor of 5.
yes, and then it will be again. Yeah. Okay. Thank you.
Actually, okay, let him go first and then Prabhu.
Okay, can you please go to the slide 5 actually?
Slide 5, okay. Yes.
Okay, so you maybe please correct me. You mentioned that this bound actually favors more compact stars, right?
Right.
So how it can be concluded actually? If you can.
No,
tell.
so more compact means smaller lambda values, and our 90% bounds are these. So starting
No,
from,
so
let's say,
compact in terms of I mean which parameter you are concluding that?
so harder to deform sort of thing. So if you want to talk in terms of lambda, so larger lambda value easier to deform, less compact, and smaller lambda value harder to deform. So in that language, from larger lambda value to smaller lambda value leads to more compact from less compact. And since the 90% bounds are below this, we say that the observations favor equation of states which give out more compact neutron star than the less compact ones.
Okay, so do you have any guess like what is the pressure or whatever for those kind of stars?
No, I mean nobody knows, but I mean we can always try to solve TOE equation for different choices. For example, here this was exactly done. So here we did not. Here we used relation which was sort of use common equation of state, but here we actually parameterized the pressure to density relation to find and solve it exactly to get the radius constraint. So yeah, I mean you can try out. We don't know what is the right equation of state, but yeah, there are.
So
good
actually,
Maybe let others ask and you can ask in the discussion. So Gopu, I think, and then you can ask in the break, I think. So request to keep your questions short and succinct, and we can discuss more during.
Very nice talk, Chandra. I have a couple of questions, but I will be very brief.
Yeah.
So the fact that you have lambda to tilde is better estimated simply because you are adding post-Newtonian corrections, so somewhat inflating the previous, the quadrupolar or the dominant lambda. Is that the way to understand that?
Yeah, I'm just completing the waveform.
Yeah, sure.
Yeah, and
perfect.
I'm expecting that it will get better, and it does get better.
Yes.
Yeah.
So with the post-Newtonian corrections to the, as you correctly pointed out, reparameterizing this.
Right.
So how crucial this will, if you have an independent estimates or different estimate for the mass ratio, better, will that be interesting implication for all these in the sense of, getting the radius things constrained?
Yeah, I mean, we do measure all this together, right? So
Sure.
if there is a system which is favoring better estimates of mass ratio, it will reflect in the tidal deformability measurement also.
Okay.
Yeah.
The last question, just is a fun. So since these are 5pn contributions,
Yeah.
you are not incorporating 4pn and the higher order point particle. So there will be a systematic bias.
Right.
Is that I know, of course, you can put parameters and maybe do it in EOB too, but they have been taken care, or they have been sort of quantified so that it will not flow into your estimates.
Well, there is always this element, right? I mean, you don't we don't even have 4pn non-spinning piece, so.
We can put it from the test particle.
Yeah, but I would like to see it as an independent effect, which you start to see only 600 hertz beyond. So if you have, so for example, we argued that the number of cycles in tidal deformability are about 2.5 or 3. If I can capture the element of these 3 cycles, we'll be happy. Okay, and it will put a constraint on this. Yes, there are 3000 more cycles and they needs to be more accurate, but to me this is a different effect that is appearing beyond 600 hertz, and you should be able to constrain despite, yes, there are always systematics, and in fact, when we look at the constraints from, sorry, I didn't, so for example, the constraints are not exactly the same as in spiral waveforms when you include the EUB waveforms and so on. So they will be slightly different, and yes, the 4pn piece should all. Yeah. So I mean, I'm hoping that it will be consistent even then. Yeah. Maybe Guillaume can answer it better, but this is the extent to which I would like to think. Yeah.
Yeah. Thanks, Chandra. The slide 9, when you look at these sensitivity levels with these different observation plans.
Yeah.
So what percentage of these planned observations are usable? Do you get affected by interference, and do you have to worry about them? Is it growing in time over years? What kind of?
This is always a concern. It's like a routine thing for us. So every data set is very dirty to look at. In fact, you would not believe if you see the first event data set. All of us know. So while we were detecting this, just before the merger, there was a glitch, and it just offsets the detector in some sense. So you have to remove these artificial elements and then have a cleaner data to look at. But Gopu, you wanted to make a remark.
Just follow. Imagine a scenario where that glitch was not there. Have you been constraining the tidal deformability?
No, I don't think. Well, yeah, probably, yes, I mean, always, but it's not that we try to model that part using, let's say, burst algorithms and replace the data. So I mean, it's not like we are losing 100% information there. But yes, I mean, given that we have essentially 3 cycles maximum, there can be an element which could have been better. Right, and this is the Livingston, which is the most sensitive detector actually. Yeah.
So this is about the slide 9.
Yeah.
So I just want to know, what is the waveform model that is implemented to get those distances or some? So since there are various waveform models.
Yeah. So this is So this is as I said, that this is assuming binary neutron star as sources, and you can use the simple in-spiral models, that the ones that I showed, to get this range.
I think 1.4 solar mass, I think, right?
These are all BNS.
Yeah, these are all BNS, like 1.4, 1.4.
Price distances are tailored.
Yeah, exactly. So you can use this waveform to calculate.
Is it depends upon the various waveform models, like which waveform model you are implementing? Or?
So this is just indicative. So we don't do, I mean, if you want to compute the horizon distance for a set of events, then you can use more sophisticated waveform where you also include the information for the merger ring down. But to just indicate that how what is the typical range up to which these detectors will be sensitive, we can use the Taylor-F2 waveforms, which are in spiral waveforms.
Okay, any questions from Zoom participants? Just quickly check. Okay, so let's thank Chandra again for a very nice talk.